Which one? Anybody guess?
Is it the correct me if I'm wrong, is it the Pearson, the one we've
Yes,
always used?
yes, yes. Up to now, in all your, in most of your classes, unless you took maybe finance 3710 with me or some other class with me sometime. I used to teach statistics. I will have mentioned it, but especially in finance 3710, I do mention it from time to time. The correlation you have learned up to now is a Pearson correlation. Pearson, okay? That is the one all of you know. Anytime we have said correlation in this class, in your previous classes, in your ECHO 4000 classes, statistic, all of those, all the correlations you have learned so far is Pearson correlation, okay, guys? And by the way, I'm going to discuss this tonight, and I have a few materials I'm going to upload to you for you on Blackboard, exactly what I'm saying tonight, okay? So I will put it up on Blackboard so you know. But I think it's unfair to everybody here, business students, finance students, economic students, that you graduate and not be able to distinguish, okay? All the correlation you have talked about so far is Pearson. What do we know about the size of Pearson? What numbers can that Pearson correlation take? What range of numbers? Can anyone remind us?
It could take anything between -1 and +1.
-1 and +1. Okay?
Yeah.
The same thing, Spearman's correlation, Kendall's tau, all of them have to be between -1 and +1 because essentially they are measures of correlation, some type of measure of correlation. Is that clear? Okay. And usually what they mean is that when one item moves up, the other one moves down on average, relative to their averages. That is what you have learned so far. Pearson correlation said, if the correlation between IBM return and S&P 500 return, if that correlation is 0.2, plus 0.2, it means that on average, when S&P 500 index moves up 1% relative to S&P 500's average, then IBM will move up by the correlation number relative to its own average. So correlation is when IBM is doing something relative to IBM's average, what is S&P doing relative to S&P's average? Correlation between Chrysler and Tesla, when Tesla is moving down relative to Tesla's average, what is Chrysler doing relative to Chrysler's average? If whenever Tesla gains, suppose Tesla's historic average is 10%, and anytime Tesla makes higher return than 10%, its historic average. Anytime Tesla gains relative to Tesla's 10% average, then Chrysler is also gaining relative to Chrysler's average. Then correlation is positive. If also, whenever Tesla is losing relative to Tesla's 10% average, then Chrysler is also losing relative to Chrysler's average. So whenever this common stock is gaining relative to its average, the other common stock is gaining relative to its own average. And whenever this one is losing relative to its average, this one is also losing relative to its average. So whatever this one does relative to its average, this one also does. Whenever this one goes down, this one also goes, but relative to their individual averages. That's what you know so far. Is that correct?
Professor, when you say average, you mean their like returns?
Okay, yes. Suppose you, for your homework, for your homework one, suppose you did Microsoft. And let us say we have data of Microsoft from 1900 until 2020. No, let's not say until 2020. Yes, until 2020. Let's just say until 2020. Month by month, from 1900 up to 2020, we have all the returns. Simple returns for Microsoft. Then let us say we measure the average monthly return for the same Microsoft, for all that data. Let us say that average return for Microsoft is 10%. So far, so good? Yes?
Yes.
Okay. So that long-term historical average for Microsoft is 10%. And then January 2021, Microsoft made 13%. Now tell me, is that higher or lower than its historic average?
It's higher.
Higher.
It's higher. In February, it also made 12%. Is that higher or lower than its historic average? It's higher. At the same time Microsoft is doing that, you look at S&P for the same period, the same long-term period, 1900 up to 2020. And let's say the historic average for S&P 500 is 7%. But you notice that every time Microsoft gains relative to its own 10%, S&P also gains relative to its own 7%. So if Microsoft gains 13%, that's 3 above. S&P maybe is 9%. That is 2 above its 7% average, but it gains. Every time Microsoft gains relative to its 10%, S&P gains relative to its 7%. But then anytime Microsoft goes like 6%, which is below its 10% average, S&P also goes below its own 7% average. If you notice that in your data, all through your data, maybe not each time, but on average, many times. It doesn't have to be each specific time. But in my example, just imagine in your mind that we are lucky that every time Microsoft goes above 10, S&P goes above 7, its own average, every time. And every time Microsoft goes below 10, S&P goes below 7, its own average, every time. Then what are we saying? That anytime Microsoft moves up above its own average, S&P moves up above its own average. And every time Microsoft moves down below its average, S&P moves down below its 7% average. What kind of correlation is that? Positive or negative?
That's a positive correlation.
That's a positive correlation. Whatever Microsoft is doing relative to its average, whether it's going up or down, S&P is also doing relative to S&P's average. That's positive correlation. And the negative correlation will be the reverse. Whenever Microsoft goes above its own 10% average, you notice that whenever that happens, S&P 500 goes below its own average, 7%. So anytime Microsoft goes above 10%, S&P goes below its own 7%. And it happens all through each time. That's a negative, and then the other way around too. That's a negative correlation, okay? We are not usually that lucky that it happens every time, but most of the time on average, that's what happens. So Pearson correlation is, on average, whenever this moves up above its average or down below its average, what is the other one doing? That's Pearson. Okay. The other two, again, whatever I'm going to say now, I'm going to show you a file that measures all of this, and I'll post it on Blackboard. But sometimes, remember in your homework one, sometimes in your homework one, we all tested for normality, right? Jacques Berra, you remember that, right? If your data does not come from a normal distribution, but your data comes from some distribution out there, sometimes using Pearson correlation presents a problem. So Pearson correlation is what we call give me a second. I'm writing on chat now, okay? Pearson correlation is what we call parametric. It's what we call a parametric statistic because we're using things like, you know, the return above its mean. The sample mean is a parameter. But what if we have situations where we need to use non-parametric? What happens in a situation where the distribution is not normal? Remember, for a normal distribution, we need only two parameters. What are those two parameters that we need to fully describe the normal distribution? We need the first two moments, yeah?
Variance and mean.
We need the mean and the variance.
Yeah.
So those are parameters. But if your distribution is not normal, then it's a whole different ballgame. That's one. So if your distribution is not normal, we may need non-parametric statistics. So the Spearman's rank and the Kendall style are non-parametric. So we use them in situations for where we cannot do non-parametric testing or in situations where we cannot do parametric analysis. That's one. Secondly, Pearson's correlation is linear. It's a linear concept. It's a linear measure of association between two variables. But what if your variables are not linear? That's a problem. So we may need other measures of association. Spearman's and Kendall's are another example. Now, I'm not asking you to know how we calculate Spearman's or how we calculate Kendall's. That's not what I'm asking, okay? If this were a statistics class, we'd do that. If pure econometrics would do that, but I don't want to do that, okay? But in the future, I think in chapter 4 or so, or if we are lucky to get into chapter 5 or for value at risk, then we may see situations where we might need non-parametric statistics. So that's where we use Spearman's rank and Kendall star. But let me say something finally, okay? Suppose in this class, if I want to measure the average height of all of us in this class, can somebody just briefly, please, I need to hear somebody else talk. Can somebody give me an idea? How can I measure the average height of all of us in this class? How?
Measure everyone's height
exactly, Alec, thank you.
Divided by the number.
Thank you so much. Okay. I was waiting for that. Okay, so there are 35 of us today here, Alec. So what do? I take a tape measure, or I say everybody stand on the wall, measure yourself. Tell me, Alec, please help me. Alec will record everybody. So Alec, height. William, height. Andrew, height. Sophia, height. Onoche, height. So we take each of us, 34 of us, we measure our height. So what do? I add up all those heights. I divide by 34. That's the average. Okay, that's parametric because we are using average height. But there are some situations in in life where I do not trust the measurement. I say, look, Alec, I love you to death, Alec, but I don't believe that you can measure the height properly. So, Mr. Alec, instead of giving me the height itself, Alec, can you please help me? Give me the rank can you rank students in this class according to their height?
Yes.
You can do that because you will say, okay, James Andrew, you are the tallest person, so James is number 1. Sophia, you are the next tallest, so Sophia is number 2. Danny, you are the next tallest, number 3. And then freaking Onoche, you are the shortest in this class, so you are number 34. Okay, now think about this. What does rank 1.5 mean? Does it have any meaning? No. So we might want to carry out some studies using not the parameter itself, height and average height, but we might want to carry out some analysis using, Alec, instead of the inches and feet and meters of height, using the rank of height, the tallest, the next tallest, and then the shortest in class. When you have to do that, you cannot use Pearson's. You cannot use Pearson's correlation, the stuff you have been using before. You can only use other measures such as Spearman's and Kendall's. Hold on a second, guys. Let me, I'm going to post this after class, okay? I have like 2 or 3 of this. I went searching on the internet for what I can post that you guys can read and understand, okay? But the bottom line I want you to know is that Pearson, you use Pearson when you have what we call ratio numbers. Those are numbers you can divide, you can multiply, you can add, subtract, and everything. But when you have numbers that show some kind of ranking, but you cannot add them up, you cannot divide them. Oh, does that mean that if James Andrew is the tallest and Victoria is the next highest, then rank 1 plus 2 equals rank 3? That means it's Selisa's height. No. You cannot add those numbers because it's meaningless. Okay, but the numbers themselves, they denote a kind of ranking. The first one is the tallest, the last one is the shortest. So there is some kind of order. I think the name of that kind of number is ordinal. And then there's nominal. So there are different types of numbers. You studied those way back when. But when we have ranking, you cannot use Pearson. So you have to use Kendall's or you have to use Spearman's, okay? So I have downloaded this for you. And I have kind of put it in a nice way for you to read and understand. So I have just given you 2 occasions where you cannot use Pearson, but the other 2 are better for you to use. So I'm going to post all of this. I'm going to post 2 Word files sometime tonight on Blackboard, and please make sure you read them and interpret them. They are very easy to, but I want you to get the meanings of this and when and how you use them. I don't need you to know how to calculate them, okay? Danny, you have your hand raised.
Professor, when we're describing and comparing each of the correlations, are we describing it to, like, say, a statistician or econometrician, or
no? You use this Word file, okay? Because I have included a comparison of the numbers, okay? Here it says the main advantage of using Kendall's are the following. So you can read this. This is in everyday language. I don't need you to be any fancy statistic. The only fancy thing I think you need to know is, you don't need to know, but you need to understand is what is meant by concordant and discordant when you talk about Kendall. Again, in time series, we use those concepts. But for this class, I will not make you, if you go to page 44 of your textbook, it gives you the formula for Kendall, but I don't need you to know that, okay? Because R will calculate the number for you. Okay, so guys, I'm going to post this and another Word file for you to read. There are other advantages and so on. So read them up. I just gave you two. One is when we have a not normal distribution, we cannot use Pearson. And number two, when we have ranking, the numbers are ranks instead of like height and measurement, the real measurement, we cannot use Pearson. Okay. Let me bring up the textbook because I want to show you. Where's the textbook? Where's the textbook? Give me 1 second. I'll bring the textbook. All right. So this is a textbook. On page 44 of the textbook. Okay. So this is the formula for Kendall's correlation, Kendall's tau. And in statistics, this is called Kendall's tau dash B. There's Kendall's tau A and Kendall's tau B. Okay. But you don't need to know that. Okay. Just use. Now, what we mean by discordant here, concordance on this line and discordant on this line. Concordance and discordant. Again, you really don't need to know it specifically, but let me explain to those of you who need to know it. The Kendall's tau, this is the symbol for tau, is kind of little Greek T. Is the probability, so I have two variables. I have X and I have Y. So maybe X gives me the ranking of IBM's return over the past 12 months. So January was number 1 in terms of return. March was number 2 in terms of return. April was number 3 in terms of return, and so on. So you are ranking, you are not ranking, you are not using returns 10%, 5%. No, you are using ranks. So in January, IBM gave me the highest return for the year. In March, IBM gave me the second highest return for the year. And so the numbers we're using now are ranks. That's X, IBM. Microsoft or S&P 500 is Y. We're not using S&P 500 returns. We're using the ranks. Maybe in June, S&P 500 gave us the largest return for the year. So June return would be number 1 rank, and so on. Concordant, meaning that when you take the difference between two ranks for IBM, they are in the same direction as the difference between two ranks for the other asset. So if going from one rank to the other, you are going negative, the other one is going negative, and whenever you rank it the other way, it's going positive versus positive, that's concordance. It's in concord, it's in agreement. The rankings are in agreement. But sometimes, yes. Okay, rank 1, yes, mine, remember, this is X, that's IBM, and this is Y, S&P 500, yes? They are two different things, right? Okay, it happens. Again, it doesn't, I'm sure you guys have never come across this, but sometimes the way we rank is different. We may rank higher return, the next higher return, the next higher return, and then that's for IBM. Then for S&P, we may rank returns higher than median return, returns higher than median, returns next higher than median. So the rankings can be different. But it doesn't matter how you rank IBM or how you rank S&P 500. If you go from rank 3 to rank 1 is the same positive as going from this rank to rank 1 for S&P 500 is positive, and negative, then they are in concordance, they're in agreement. But sometimes, depending on how you rank, okay, when this one, the difference in the ranking is positive here, the difference in the rankings can be negative here, and vice versa. In that case, they are discordant. They are in disagreement, so to speak. That's roughly the way to explain concordance and discordance. But again, I don't need for you to know this. All I want you to know for now is, interpret those numbers. Those numbers must always be between -1 and +1 because they are all correlations. When do we use them? We use them when our conditions for parametric don't hold, okay? I want to move on quickly. I'll post all of this for you so you can read them and better, okay? And then you can ask me on Thursday. I'll discuss it again with you on Thursday, briefly, okay? All right. But this, remember I gave you the page numbers. These are the commands to calculate the Pearsons, the Spearman, and the Kendall. So just give these commands, you get those numbers, and then you move on from there. All right. One final thing I want to show you is, and then, oh my God, time is always of the essence. All right, where's homework number 2? Where's my, give me a second, I'll bring up homework number 2. Okay. All right, so that's this one. For number 8, I did an example with you for number 8. But in the example, I use confidence interval for number 8. Okay, again, let me show you what I mean. In class, we did, give me a second. All right. Okay, this is on Blackboard. I did this problem with you in class. Does anybody remember this?
Yes.
Okay. So this example, I tested individual. I built confidence interval up and down for each of these, and I said everything for lag 2, the autocorrelation was in between that interval. For lag 3 and lag 4 and lag 5, only lag 1 was outside of the interval, so it was significantly different from 0. So essentially, that's what I'm asking you to do here. But for the homework, you have to use R. Okay, so the R commands and the T test are all on page 47. And then for number 9 is the box Pierce and the Leon box. I did that example for you. It's on Blackboard. So look at the calculations, and then if you use R, the R command is on page 47. You don't need to do the calculation yourself. R will do it, and then you can interpret it. And then number 10 says, based on your number 9 and your number 8, are these white noise series. You can figure that out. We discussed that in class. So I move on. Roxolana, I will not give you specific answers to this question if that's what you want to ask, but.
No, I just wanted to ask if it's possible, because this is what I got for my thing. Is it possible for box Pierce and Lee Young box to give you like different results?
Of course, the example I did in class, did we get the same result?
No, by different results, I mean like
different conclusions.
Yes, different conclusions.
Well, it's not impossible.
Only for some lags, not for the entire.
It's theoretically, yes.
Okay, thank you.
Because don't forget, the formulas are different. That's why first I did the formula with you in class, and the formula is in the book on page 49, but I worked an example with you in class. Remember that, right? So you should be able to answer these questions, okay? All right, can I move on? Any other questions? All right, I need to teach class tonight, okay? Please, guys. again, do this and bring your questions to class on Thursday, but this is quite doable for all of you, okay? All right. What time is it? 6:40. If you go to your Blackboard at 6:15, I uploaded 1, 2, 3, 3, 4, 5, 6, 7. I uploaded 5 pages of proofs for autocorrelation of AR1. So you want to go there now? Okay, you guys have it? I have it here, so I'll share it with you. All right, let's see. Okay, all of you should have this page on Blackboard now. I put it in to activate at 6:15 because I thought I'll be done discussing the homework at 6:15, but not. But that's okay. Have you seen this, anyone, from your Blackboard?
Just downloaded it.
Okay. All right, it's there. So, but you don't, let me just go ahead and discuss it now in case. If you understood what we did in class last week, Thursday, can anybody remind me what did we do in class last week, Thursday? I showed you the proof of the formula for variance of an AR1 process. Is that right?
Yes.
Okay. And I said that formula was the variance of an AR1 process. It's also the autocovariance at lag 0. You agree, yes? Because the variance is the same as the covariance, is the same as the autocovariance at lag 0. Everybody agrees with that, yes?
Yeah.
Okay, good. So that's why I'm not saying here, I am not beginning with lag 0. Because we already did lag 0 last Thursday. Okay? Yes. Lag 0, the autocovariance at lag 0 is the variance. So everything we proved in class last Thursday is the same as autocovariance at lag 0. If you notice, those 2 pages I gave, I numbered them page 1, page 2, and this one is page 3, and then the next one is page 4, because they should all be together. Okay, if I wanted to, if we were in the classroom, I'll just prove everything together. I'll say, after proving the mean equation for AR1 process, I will just prove the autocovariances and autocorrelations at all the lags for an AR1 process, beginning with lag 0. But lag 0 is the same as proving the variance. Okay, so we did that. So today I'm going to begin with the autocovariance at lag 1. This is how we represent autocovariance, gamma. So gamma sub 1 means autocovariance at lag 1. Guys, if you remember, if I have 2 variables, x and y, what is the covariance between x and y? I write covariance x comma y, parentheses. Yes, you remember that, of course. That's how we write covariance. Covariance between x and y, 2 different variables. But when we're doing with univariate time series like we're thinking of only Microsoft's return. So it's only Microsoft today, yesterday, 2 days ago. So today is x sub t. The return today is x sub t. The return yesterday, x sub t minus 1. The return 2 days ago, x sub t minus 2, and so on. So we're dealing with only Microsoft. We're not dealing with Microsoft and S&P 500. No, we're dealing with only Microsoft. So that's why we don't call it covariance, we call it autocovariance because it is covariance with itself, but just different time periods. Okay, so anytime I write COV here, I really mean autocovariance. This word is too long, so I just shorten it by co. So the covariance between xt and xt minus 1. What is the covariance? Again, let me back up to what you learned in 3710 and Echo 4000. What is the covariance between variable x and variable y? The covariance between variable x and variable y is x minus the mean of x, y minus the mean of y. We multiply them together. So we do it for each observation of x and y. We add them all up, and then we divide by n, or divide by n minus 1. It's when you add many, many things up and you divide by the number of things you added up, you are taking the average. So the covariance between x of t and x of t minus 1 is really the expectation. When we say the expectation, we mean the average. The expectation, the average of xt minus its mean times xt minus 1 minus the mean of xt minus 1. Okay, you guys, you agree, right?
Yeah.
Okay. Who said yeah? Danny, right?
Yeah.
Okay.
It's just instead of y minus the average of y, you're just putting the sub lag 1 basically.
Exactly. That's what makes it autocovariance, because this is about the same IBM or the same Microsoft, but at different time periods, today and yesterday. Is that correct?
Yes, sir.
Okay, good. I can rewrite this. I can remove the averages. I can remove the averages. Why? Because we set up that the constant for, remember last Thursday, the AR1 we used didn't have constant. Yeah. We made the constant 0. Everybody remembers that, right?
Yeah, and made the average 0 as well.
0,
right?
yes. We made the constant term, the first time 0. And therefore the expectation is 0. We showed that last week. So that makes our lives easy, because then we do not have to carry these averages in between. Okay, so that is this.
Well, Professor, that's for simplicity. That's not always the case. It's just the mean has to be constant, right?
Yes, that's just for simplicity. But there's no way in, you know, that in this class I will have you prove this when this is not 0. Okay, that's absolutely no way.
Wait, prove what?
There's no way I can do everything I'm going to do with you tonight without setting this to 0. I mean, you guys are going to throw me into the Hudson River. Okay.
Okay, I just wanted to make sure that it doesn't have to be 0. Okay, it just has to be constant.
It doesn't have to be 0. Is this Danny? Yeah.
Yeah.
It doesn't have to be 0 at all, because our AR1 equation doesn't have to make that first term 0. Okay, this is just for convenience. Otherwise, the proof would be a problem.
Got it.
Okay. So when we do this, then now we can apply steps as we use for variance. So this equals covariance of this. We have equals this. We have removed the means, the mean of t and the mean of xt minus 1. If we do this, then this is exactly the same thing as we did last Thursday. The difference, now everybody please just stay with me, because I am going to bring up what we did last Thursday in case you've forgotten, okay? Now, when we were proving variance last week, what is variance? Is gamma to 0. is autocovariance at lag 0. Is that correct, everybody?
Yes.
Okay. If we're proving variance, this will be gamma to 0. Then it will be covariance of xt and xt minus 0. So it's xt and xt. So that would be expectation of xt and xt. So last Thursday, we did it with xt here and xt here. And then we got something like this last Thursday. But last Thursday, wherever we had xt minus 1 and so on, it was different. So let me go back and show you. Don't go anywhere now. Let me bring up what we did last week. Hopefully I can find it. You have it. You have those 2 pages from last week. So let's see. I believe, let me check this. Okay. So this is the first page I showed you last week. The first of 2 pages we used when we proved variance. I just called it variance last week because, but I could have said autocovariance at lag 0. So autocovariance, look at this. It's expected xt minus mean of xt and xt minus mean of xt. Because variance is autocovariance at lag 0, this t minus the lag is t minus 0. So this is xt. And so variance is really, we're squaring the same thing. Is this times itself, that's squared. But I wrote it this way so as to prepare you for today's lecture, for autocovariance. So when we used this and we made this 0 and this 0, and therefore we had ext of an xt, then we went here and proved this. At the bottom of this page, we arrived at this equation. Therefore, x of t, with my little digression, x of t is mu of t plus the 0.9 in my example last week, the factor here, the coefficient of ut minus 1 and ut minus 2 and so on and so forth, okay? But what happens, guys, if this is not xt, but what happens if this is xt minus 1? Then this will be ut minus 1. And this will be...
everything moves 1 lag.
Thank you. Thank you. I owe you a coffee next time I see you, okay? So everything moves 1 lag. So I'm going back to our today's proof. So everything moves 1 lag, which is what we are doing today. So here now is xt, and this is not xt, but this is xt and xt minus 1. So for this one, we still retain xt. So it's this one, ut plus t minus 1. But for this one, everything moves 1 lag. Thank you so much. That must be Danny that said it. You saved my voice. Thank you. So here applies to ut minus 1. Here applies to xt. Last week, it was xt here and xt here. So whatever we had here too last week. But that's not today. So for the autocovariance between xt and xt minus 1, we just shift everything here by one lag. And then we multiply out. Okay? What is everybody tell me here, what is the average of, what is the expected value of this white noise process?
0.
0.
Or, yeah.
It is 0. So that if I open up this parenthesis, so here I'm multiplying everything here by everything here. So I'm saying ut and then take expectation. I wouldn't do that because it's all 0. So I'm not bothered with these white noise processes at the beginning. I just start here. So phi1 ut minus 1 times ut minus 1. So it will be phi1 ut minus 1 squared because I'm multiplying ut minus 1 with itself here. That's this one. Then phi1 ut minus 1 times phi1 ut minus 2 is phi1 squared, ut minus 1 and ut minus 2. But you remember I said on Thursday that when I take expectation when I bring expectation of ut minus 1 and ut minus 2, two different lags, what happens to that result? It becomes 0. So I expand this by capturing only where I have ut minus 1 squared. So this one and this one. And then where I have ut minus 2 squared multiplied by itself. So I multiply this by this. And where I have ut minus 3, this. And any other place I have ut minus 1 and ut minus 2. Like, for example, I multiply this and this. I multiply ut minus 2 and ut minus 3. Anytime the time lags are different and we take expectation, they all zero out. So that's why I bunch them here. I said cross products. Cross products are all the terms that have ut and ut minus 1, ut minus 1 and ut minus 2, ut minus 1 and ut minus 3, ut minus 3 and ut minus 4. All are cross products because when I open up this parenthesis and hit all of them with E, everything, you see, well, if I open up this parenthesis and take E of this, E of this, E of this, and then E of this cross product terms, everything goes to 0. My God, that makes our life so simple. Hey, Danny, you still there?
Hanging on.
Yes, hanging on. Alec, you're hanging on, I know. Andrew, you're hanging on. You guys, I know all of you are hanging on. That's why, okay, of course I know you're here. So that's why I put everything as cross products, okay? So that when I hit E with cross products, everything goes to 0. The things that do not go to 0 are when I have ut minus 1 and ut minus 1, ut minus 2 and ut minus 2. So I'm squaring them. So all of this I keep. So that, and don't forget so when I multiply this by this one doesn't have the coefficient. So it will be phi 1 ut minus 1 squared. That's this one. When I multiply this by this one, it will be phi 1 squared and phi 1, that's phi 1 to the power 3. And ut minus 2 and ut minus 2 is ut minus 2 squared. So I just hold on to where we have ut minus 1 squared, ut minus 2 squared, ut minus 3 squared, ut minus 4 squared, and everywhere I have ut minus 1 and ut minus 2, ut minus 1 and ut minus 3, ut minus 2, I put them all as cross product because when I hit them with the expectation, everything zeroes out. So my life is easy. Okay, so it boils down to this one, this one, this one, plus phi 1 7, plus phi 1 9. So these are all going up by 1, phi 1 to the power 1, phi 1 to the power 3, phi 1 to the power 5, 7, 9, 11, and so on and so forth. Da, da, da. And everything else that have cross product of the UTs, 0. So my gamma, so my autocovariance at lag 1 will be equal to this expression. Because guys, the expected value of what is the expected value of white noise squared? That's the variance of the white noise. What do we know about the mean of white noise process? Is 0. We assume it's 0. What do we know about the variance of white noise process? Is homoscedastic. Yes, it is constant.
Constant.
So whether it's t minus 1 or t minus, whether it's 1 lag or 2 lags, it's constant for white noise. So that's why expectation of this is the variance of t minus 1 is constant. Is the variance of the white noise lag 2 is constant, the same variance, the same variance. Look, I didn't put t minus 3 here, t minus 2 here. No, it's the same number because it's homoscedastic. When it begins to change, then we are in chapter 4 of your textbook. That's where we do arch and gotch, autoregressive conditional heteroscedasticity, because then it's heteroscedastic, it's changing over time. You understand? But for white noise, if it's homoscedastic, it's constant. It doesn't change. It doesn't matter what the lag I'm considering is. Okay, so I'm going to move to the next page. Okay, everybody stay with me. That's page 4 now. Page 1 and 2 was for variance last Thursday. This is page 3. I'm going to move to page 4. You have it already on Blackboard. So I'm going to look for it now. Sorry, my desktop is such a mess. It takes me a long time to find it. Hold on, I think this is page 4. Okay, so this is page 4, exactly. All right. So from the previous page, I want to simplify a little bit further. So I bring out phi 1 and sigma 1 squared, and I have 1 here. I have sigma 1 squared, I have sigma 1 4, and so on and so forth, okay? And then, look, remember some time ago when we were proving the mean, I said from calculus, I know you guys don't remember, it's okay, it's a long time ago. From calculus, this is what we call an infinite series. When you have an infinite series and you're adding them up, the result is, the first one is 1, because this one is 1, the first term here, divided by 1 minus the constant term by which each of this is increasing. What is the constant factor of increasing here? Anybody tell me?
Phi 1 squared.
Phi 1 squared. Because 1, I multiply it by phi 1 squared, I get this. I multiply this by phi 1 squared, I get this, and so on. So it's 1 minus this, phi 1 squared. So the autocorrelation at lag 1 is equal to this. Okay, guys? Does anybody remember? I don't know if you have your class note with you. What was the variance of an AR1 process? What was the variance of an AR1 process? It looks something like this, right? Except that there's an additional term here.
Professor, you said variance or autocovariance?
What is the variance that we proved last Thursday? Variance, remember the variance is autocovariance at lag 0, yes?
That would be phi squared over 1 minus phi squared sub 1.
Are you sure? Was that phi squared?
Or sorry, is that standard deviation?
Yes, that's sigma squared, right?
Yeah.
Divided by, but in this case, at lag 1, we introduce the phi 1. So this is almost the same as the variance, except that the difference is this term here, yes? The phi 1. Just look at the bottom of page 2 from last Thursday if you still have it available to you, okay? If you don't, I have it. So let me show you. So this is from last Thursday. This is page 2, okay? And look at the bottom here. This is the variance. Oh, you can't see this because it's too small. Let me make this a little larger. So this is what we discussed last Thursday. So the variance of the AR1 process, x sub t, the variance is sigma squared. Sigma squared is the variance. What is this sigma squared? Is the variance of what?
Of the white of the error term.
Exactly, thank you. Is the variance of the white noise error term. So the variance of the whole process is the variance of the white noise process, which is homoscedastic, which is constant, divided by 1 minus the phi 1 squared. Phi 1 is the coefficient of the xt minus 1 of the lag variable. Okay? Now, so this is variance of xt, which is the same thing as autocovariance at lag 0. Okay? But autocovariance at lag 1, now this phi, we bring phi 1 here, not phi 1 squared. We put phi 1 here times this divided by this. That's what we just showed today. Okay? So let me go back to it. That's what we just showed here, okay? So the autocovariance at lag 1 is phi1 times the variance of the, oh my God. Nobody told me that I've run out of time. Okay, give me just 2 minutes and I'm done, okay? So it's this one, okay? Autocovariance at lag 2, what do we do? Expected xt minus xt minus xt minus xt and xt minus 2. So the autocovariance at lag 2 is xt and xt minus 2. Remember, for this one is xt and xt minus 1. This one is xt and xt minus 2. You use the same logic, exactly the same logic, and then you get the result. Let me show you the result. Just give me 1 more minute, everybody. What is the result? It will be here. Okay, autocovariance at lag 2 is, again, phi, this is phi1, this should be subscript here, it should be phi1 squared. So without this phi1 squared, you have this one is exactly like the variance. So at lag 1, we add phi1 to 1 to power 1. At lag 2, we will have phi1 to the power 2. At lag 3, okay, it will be phi1 to the third power, phi1 to the third power with all of this. At lag 4, it will be phi1 to the fourth power. That's exactly what we show for the rest of the proof, okay? And then after that, we convert it to autocorrelation. So guys, I'll finish this up next class, okay? And then, so look at that. So at lag 3, at lag 4, at lag 5, at lag 6, so, and at lag S in general, autocovariance at lag X will be phi1 to that lag times everything here else is the variance. Okay? And then the next thing I'll show you is then we convert autocovariance to autocorrelation by dividing by variance. And then we get the result, the final result that I'll finish this up on, I'm sorry, this is not what I want. I'll finish this up on Thursday. I think this is what I want. All right, I'm kind of messing. Don't worry, I'll finish this up on Thursday, okay? Don't worry about it. So these are the two things I'll do on Thursday. On Thursday, I'll finish this up, and I want to introduce you to the concept. So far for AR1, we have shown the formula for the mean. We have shown the formula for the variance. And I started to show you the formula for the autocovariance and autocorrelation at different lags. I'll finish that up on Thursday. And then on Thursday, I will introduce you to something called not autocorrelation, but partial autocorrelation for AR1. I will not show you the proof at all, but I'll just give you the result and show you the graph. Because generally, when we want to identify whether Microsoft follows an AR1 process, a very neat way to do it is to plot the autocorrelation function ACF and then the partial autocorrelation function PACF. So I'll do all of that on Thursday, okay? All right, I'm going to stop recording now.
The recording has stopped.
Everybody, I'm sorry I kept you a little later. Thank you for your attention. I just barely shoved in everything at class time. Okay, any questions? So the class is ended, guys. Yes. Yeah. Yes, of course. I'm just showing you the equations, then I'll use the example. But when we go to moving average and we go to other, I will not be proving them like this. I'll just say, do you remember how we proved it for AR1? This is an econometrics class. So I have to show you the proofs, and then subsequently moving averages, ARMA, I will not be proving all of this like this, but I'll say, you remember how we proved this for AR1, okay?
Professor?
All right, Shijie, yes?
You go ahead, Alec.
No, it's okay.
Professor?
Yeah, I was
Yes.
gonna say very briefly that I will try to complete most of the homework today. If I have questions could I email you, or do you want me to bring the questions on Thursday?
Bring the questions to class on Thursday, okay?
Okay, thank you.
Yes, because I'm getting so many emails, and I'm just saying, and all your questions are about the same range, believe it or not. So I'm just saying, I'll look at all and I'll come to class and I will try to iron it out.
Professor?
Yes, Alec.
Does the teaching assistant know about the homework? Can we ask her questions about it?
Which homework?
Homework number 2 that you've shared with us.
She's not going to answer questions on homework number 2 until after I give you back the grades.
Well, so I had a question about the charts. Do you want us to show both of the graphs in the same chart, or
it's up to you? It's up to you. You can show them on the same graph or on different graphs. But again,
you want to see them, or you just want our description like last time?
No. I would like to see them, but in the file that has your command and your results.
Okay.
And then your description in the one pager.
Okay.
Okay. But wait, Alec, you can put 2 of them on the same page in the Word file, relevant Word file, or you can leave them separately. That's okay.
Okay, it doesn't have to be both graphs in one chart, and then because
No.
we have two charts to show, and then each of them has two graphs within the chart.
Yes.
Okay.
Okay.
But you can accept 4 in total then, right? Is that what you mean?
Yes, I can accept 2 on one graph, 2 on another graph. Yes.
Okay.
But again, if you are not familiar with R, just give me separately. That's fine.
Okay, I appreciate that.
There should be like in R you can.
All right, see you. Yes, somebody else had a question.
I have just a quick question. So you mentioned the TA isn't going to answer questions regarding this upcoming homework for us?
No, she doesn't.
Okay. I thought the whole point of the TA was to kind of guide us in that.
The whole point of the TA is to help you, guide you towards what you didn't understand with homework 1. So this week she's going to discuss homework 1 fully.
Okay.
The essence of homework 2 is for you to come to class. I teach as much as we can, and then I give you homework, and then you figure out with your class notes, with the video, and then if you need to go search outside there, you go search. That's fine.
Okay, it seems a little redundant, but all right. I mean, I'll try to get through this homework too. I just I don't want to make a huge mistake as I did on the last homework.
Well, if you follow the questions I asked you, and if you are in doubt, if you see her whenever her office hour is either Wednesday or Thursday this week, then she will go over with you how you should have answered homework 1. And homework 1 is just similar to homework 2 in the way I asked it. So if you understand what she's going to explain with homework 1, then homework 2 will be a piece of cake for you. You understand, Lily?
I do. It just seems like homework number 2 just seems like way more complicated for me to understand compared to homework 1, and I feel like
why is it more complicated?
Well, there's just the autocorrelation, like number 8 on the homework. Like I know we just like went over this in class like just now. It's just I would have appreciated the ability to like kind of go over it with her before like getting a solidified grade.
Wait. The autocorrelations, I already did a problem in class.
Yes.
And we also did box pairs and box and Leon box in class.
No, totally understand. I just want to make sure I'm doing this all correctly in R, because it's a completely different thing of understanding the concept than doing it in R. You know what I mean? Like, so I think that's more of my worry, but I'll just, I'm just going to work on it.
Okay, but Lily, before you go, okay, the essence of me recommending this textbook is that this textbook, unlike other textbooks, does examples word for word the way I want you to do it for homework.
Oh, I'm really not fine. I feel like that you're telling me that I should just be copying straight the R, because I feel like I'm not finding the R code for specifically what you're asking. Like I'm trying to figure out like even just like literally the first question of just like downloading adjusted data, like importing it. I have to like convert it into an XTS file. It's just not in the textbook. So I'm like going into like Google and like other like coding websites to kind of help with that. So hopefully I'm kind of doing this right. I'm not sure if anyone else feels like the same way about this.
Yeah, Lily, I feel you. I actually totally agree with Lily.
Okay. All right.
Yeah.
Okay, excuse me. In Echo 4000, you guys did regression analysis in Echo 4000. Yes?
Yes, but it was very much guided of what I was doing.
Okay, but in Echo 4000, you downloaded data into Excel, and then you ran what am I called? You ran the regressions on. So you can download data into Excel. You can.
Yes.
Okay, and then when you download data into Excel, I just showed you about CSV.
Yes.
Wait. I discussed CSV in class many weeks ago, but okay, we've forgotten that because this homework is coming now, but that's why I reviewed it tonight.
No, I totally understand CSV. I've been doing that, like I've done that in R before. The whole thing is that you can't actually use chart series with an CSV file. It has to be XTS-able. That's what the error says. So now I have to convert it from CSV into XTS without actually the file being XTS on my like desktop.
Okay,
so like, this is just like this, but this is just like the whole point is just like this is just like little stuff.
Okay, but Lily, hold on. If you CSV that file and you bring it into R, then you can use chart series on it, because if you bring it into R, then you're back to what you did for homework 1.
Yeah, I'm using quantmod get symbols.
Yes.
I'm just like, again, like but the whole point is just like I would like someone to be able to kind of like make like just like check my work and make sure I'm like kind of on the right path, because like I got a decent amount of points taken off on the last homework, and I feel like it was because of these things that were just like little errors in my code and just like. So again, I'm just going to work on it. I'm going to come back to you on Thursday.
Okay, come back to me on Thursday. But the point I like to make always in this class is that this class is not about R. When you guys did Echo 4000, yes, maybe some professors guided you with Excel, but others did not. There are some many of you in this class are much better at R than others. But that's okay, because in Echo 4000, many of you were much better than others with Excel. This class is not about Excel. This class is not about R. The professors who have taught this class in the past, they simply told you, go to YouTube and figure it out. But I'm doing better than that. I'm choosing a textbook where the textbook has run the R. Yes, you still have to work on it. Yes, I agree. Yes, it's not about R, but you still have to work on R. But that's where a lot of the work will depend on you for R. Because no matter how much I teach R here, we can never cover the whole of R in this class. Forget it.
Totally understand. I completely understand everything you're saying. And like, I think all of us are doing our best to kind of catch up with whatever we don't know in terms of R. I just like, in terms of what we do in class,
yes,
as you said, this isn't a coding class, right? So like,
and for example, tonight as a professor, I feel frustrated because I spent less than half the class on econometrics tonight.
No, I totally understand.
And I'm talking about homework, and I'm talking about R, and I mean, and many of you are here to learn econometrics.
Yeah, it's unfortunate. You know what I mean? It's kind of, you know, it's unfortunate. It just, our homework is in R, and that's what we're being graded on. It's not. Yes. So we're just gonna have to figure it out.
Again, I'm not grading you on your R abilities in this class. I'm not, totally not. I'm grading you on your understanding of the concept.
I respectfully disagree that you're not grading us on the R. But like,
I'm not grading you on the R because for the homework, some of you plotted the graphs, but when I say explain the graph, that's not R.
So you're going to weigh more heavily on our explanations of the graph, even though the graph could be wrong, because I could be doing something wrong in R.
If the graph is wrong, but how can the graph be wrong when all you need to do is to chart series, Lily? I mean, I give you guys more credit than you seem to give yourself.
Yeah,
It's just honestly, I need you guys to please, I really need you to, again, I need everybody to stay with me here and not freak out because of R. This is an econometrics class. Okay, this is about econometrics, not about R. Okay, I want to really tell you that.
Okay, I wish the TA would be able to help us with homeworks other than what we've already been graded on, because it feels
if you go to the office hour, last homework you will use chart series. Last homework you use quant mode. You can ask her those questions, but
okay.
if you want for her to confirm or deny your answer for homework 2, she will not do that.
No. That's not even what I'm asking. That's not what I'm asking, Professor. It's more of guidance of certain, like, I don't even know if they're called functions in R.
Okay, she will guide you on that based on what we did in homework 1, which is almost similar to homework 2.